Hi everyone, welcome to Integral Calculus. Today we explore lesson 8.3, moment and center of mass. Number one, moment of mass. Imagine that we have a rod and we put the two sides with two masses, M1, M2. Somewhere on the rod, there's a point. We call it the balancing point. And at this point, there's a distance D1 from mass 1 to the balancing point and a distance D2 from the balancing point to the second mass to balance the rod. M1 D1 has to equal to M2 D2. This equation is called the law of lever. We can put the rod on the x-axis. If we put it on the x-axis, then that is what we have. M1 and it is M2. So M1 is at X1, M2 is at X2. The balancing point is the center of the mass, X bar. From here, we see that the distance D1 is X bar minus X1, and D sub 2 is X2 minus X bar. Using law of lever, then we have M1 X bar minus X1 equal M2 X2 minus X bar. Distribute, and we're gonna solve for the center of mass. M1 X bar minus M1 X1 equal M2 X2 minus M2 X bar. M1 X bar plus M2 X bar equal M1 X1 plus M2 X2. So we can factor out an X bar here. And then we can simply divide both sides by M1 plus M2. This would give us M1 X1 plus M2 X2 over M1 plus M2. Wow, have a nice formula for the center of mass. M1 X1 plus M2 X2. They are called moment of masses. What if we have a system of masses M1, M2, Mn, and they are located at X1, X2 up to X sub n? Then the center of mass, X bar, it would be the quotient of the moment of mass summation I equal 1 to n mi xi over the sum of all the masses I equal 1 to n m sub I. We can shortcut the moment of masses as m, the bigger m, and the sum of all the masses, the smaller m. And from here, Moment of mass is the center of mass multiplied by the sum of all the mass. Now, this capital M is called moment of the system about the origin. And if we have a system of n masses, m1, m2, up to m sub n located at points x1, y1, x2, y2, up to x sub n, y sub n, respectively, then we have moment of masses about the x-axis, which is the sum equal 1 to n of the product of the mass and the distance to the mass. Well, if you look at the point on the xy plane, we have a point here. The distance to the x-axis is this distance, so that is exactly y. M sub I, y sub I. The number measures the tendency of the system to rotate about the x-axis. We also have m sub y, which is the moment of the system about the y-axis. And that is summation equal 1 to n of mi. The distance to the y-axis is xi. And the number measures the tendency of the system to rotate about the y-axis. 2. Moment of mass of a lamina or thin plate and its centroid. We can model the thin plate using a function fx. The area below the function from x equal a to x equal b above the x-axis can be seen as the thin plate or the lamina. Next step is, well, the moment of mass is different at each strip. So we can compute the moment of mass about the x-axis and about the y-axis for a sample strip and use integration to add them up. And therefore, we're going to get the moment of mass of the plate. Let's take a look at a sample strip here. This point right here is x. The output is fx. Well, the center of the strip, this is the rectangular strip, so it's right in the middle. And so in the middle is half of fx. Okay. Now, from the previous example that we did, moment is mass times distance. So this is the definition of moment. We can do moment about y-axis. So that would be mass times distance to y-axis. Mass is density multiplied to area, because this is of a thin plate. Distance to the y-axis, according to this, is x. Density is constant, so rho. Area is length times width. The width is the small change in x. Dx, the length is fx. Rearrange it, make it look a little nicer here. Rho x, fx, dx. And so the moment about the y-axis of the plate is integral, and we're going to integrate these sample moment from A to B of rho x fx dx. Similarly, we can compute the moment of mass about the x-axis. Well, that's mass time distance to x-axis. Mass is the same as density times area. So it's going to be a rho fx dx. The distance to the x-axis is, if you look on the graph, you see that it's half of fx. Okay. So there's the half of rho fx square dx. And so the moment about the x-axis of the plate, we got to sum up all these sample moment. Integral from A to B, half of rho fx square dx. Yeah. We know that mass is density times area, right? Since mass is density times area, the centroid is defined as, or the center of mass, x bar, y bar is, x bar is moment of mass about the y-axis over mass. And that would be integral A to B rho fx dx over, well, rho times the area, which is 1 over A integral from A to B fx dx. Y bar is moment of mass about the x-axis over mass, and that is integral from A to B half rho fx square dx over rho A. We have two different types of region, a type 1 region and type 2 region. So in type 1 region, x bar would be 1 over A integral of A to B x times the difference of fx minus gx dx. Y bar is 1 over 2A integral from A to B of the difference between the fx square minus gx square dx. And for type 2 region, because we would be doing the integration with respect to y, we switch the x bar and y bar. So y bar would be 1 over a integral from c to d y times the difference between fy and gy dy. X bar would be 1 over 2a integral from c to d mod of fy square minus gy square times dy. Just have to be a little careful on the type 2 region. Let's take a look at an example of each region. First example, find the centroid of the region bounded by y equal x and y equal x squared. So here come y equal x squared, y equal x. This is the area. And the intersection is from 0 to 1. Area, integral from 0 to 1. Function above x minus function below x squared dx. So this will be x squared over 2 minus x 3 over 3. Evaluate from 0 to 1, which gives us 1 over 2 minus 1 over 3. And that is 1 over 6. Now we can figure out x bar. According to the formula, this will be a type 1 region. So it's 1 over a integral from a to b x fx minus gx dx. So this will be a 1 over 6 integral from 0 to 1 x. The function above is x, below is x squared dx. So this is 6 x 3 over 3 minus x 4 over 4. And do the substitution, we have 1 over 3 minus 1 over 4. Plug this in the calculator, and that gives us 1 over 2. Now, y bar is 1 over 2a integral from a to b fx squared minus gx squared dx. So then 1 over 2 times 1 over 6 integral from 0 to 1 of x squared minus x squared dx. Okay. And we have is 3 x 3 over 3 minus x 5 over 5 integral from 0 to 1. So 3 times 1 over 3 minus 1 over 5. And this gives us 2 over 5. We can plug the point into the graph. So half is right here. And there is 1. So 2 over 5 is somewhere. Two over 5. The centroid is going to be right here. It's the center of the mass. Okay, let's take a look at another example. Okay, in the second example, we want to find the centroid of a lamina formed by the region between the curve x plus y equal 2 and x equal y squared. Well, because x equal y squared, it will be best for us to solve for x here. So x equal 2 minus y. Let's graph them. X, y. So x plus y equal 2 is just a straight line. And then the other one is a parabola. Okay. X equal y square. Oh, yay, this is a type 2 region. So we have to figure out the intersection. Okay. Now to figure out the intersection, y square is 2 minus y. So I mean y square plus y minus 2 equal to 0. Y plus 2, y minus 1 equal to 0. So y equal negative 2 and y equal 1. Negative 2, 1. Okay, from here we can figure out the area. The area is integration from negative 2 to 1 function on the right side. That would be the straight line 2 minus y minus the function on the left side, y square dy. And this would be a 2y minus y square over 2 minus y3 over 3. Evaluate from negative 2 to 1. So this would be, well, 2 minus 1 over 2 minus 1 over 3 minus, okay, plug in negative 2 in there, negative 4 minus 2 plus a over 3. Put this in the calculator and we have 9 over 2. Okay, so now we can figure out x bar and y bar. Take a look at y bar first here. Y bar is according to the formula. That will be 1 over a integral from c to d y multiplied by function on the right side minus function on the left side. So fy minus gy dy. And this would be a 1 over 9 over 2 integral from negative 2 to 1 y minus y minus y square dy. So we have a 2 over 9. This would be a y square minus y3 over 3 minus y4 over 4. Evaluate from negative 2 to 1. 2 over 9 multiply 2, 1 minus 1 over 3 minus 1 over 4 minus, plug in negative 2, we have a 4 plus a over 3 minus 4. Work out the arithmetic and we have negative 1 over 2. Yeah. Next is x bar. So this would be a 1 over 2a integral c to d fx square minus fy square minus gy square dy. So that's 1 over 2 times 9 over 2 integral from negative 2 to 1, 2 minus y square minus y square square dy. So this gives us a 1 over 9 integral from negative 2 to 1, 4 minus 4y plus y squared minus y to the fourth dy. And this 1 over 9, 4y minus 2y squared plus y3 over 3 minus y5 over 5. Evaluate from -2 to 1. So this will be 1 over 9. Plug in 1, where we have 4 minus 2 plus 1 over 3 minus 1 over 5. Plug in -2, we have minus 8 minus 8 minus 8 over 3 plus 32 over 5. With the calculator, we have 8 over 5. Yay! So let's locate the centroid. 8 over 5 and -1 over 2. Thank you for watching. I hope you find the content useful. Please like, subscribe to every channel growth. I'll see you in the next video.